All right, this is Professor Cummings. I wanted to go with one more rule of derivatives, and this one I want to discuss the chain rule. Now, we've already discussed the product rule, we discussed the quotient rule, and we discussed the power rule. And that's a way of taking the derivative of more complicated uh, functions, usually combination of functions that you would normally have a difficult time taking their derivative. In this case, you have a function that has a specific type of a format to it that we get to for this chain rule. Now, what you have when you're applying the chain rule is you have a function within a function of some capacity or another. So in this case, you've got a function. We're just saying h of x is equal to f of x, or excuse me, f of g of x. So you've got g of x is a function in itself, and then you get it within a function of f of x. And the way you would take its derivative is through the chain rule, and the way you would do that, also it's called the inside-outside rule. So the way you would do that is by taking the outside derivative, leaving the inside alone. So you're taking the outside, leaving the inside alone. So the derivative of x, or derivative of f, and then you're multiplying it by the derivative of the inside. So derivative of the outside while leaving the inside alone, derivative of the inside leaving the or just the derivative of the inside. I also in classes like to call this, the nesting doll rule. So because there's one within the other, within the other, within the other, like a nesting doll. Now, one thing about this chain rule is just like any other rules of derivatives, they ultimately are based on the power rule. And you're going to see the power rule creep up in all of our examples. So these first two examples, I have them already worked out. You have a problem, and then I gave you the solution down here. In both cases, a problem, and then you got the solution. What I want to show you in these two examples, I'm going to give you the information in the middle here. So how do I get from here to here using that chain rule? So in this case, you've got y is equal to sine of x squared. So the y is equal to sine of x squared comes out, you're looking at, as far as the chain rule goes, you're going to take the derivative of the outside, then you're going to have to take the derivative of the inside. So the derivative of the outside, which is just the sine of x, or just a sine function, and then the derivative of the inside, which is just x squared. So the derivative of the outside, sine of x, or sine of x squared, leaving the inside alone, is just the cosine of x squared. So the derivative of the outside, leaving the inside alone. And then you've got the derivative of the x squared, which in this case would be g of x, or would be analogous to g of x. So the derivative of x squared, then, which would just be 2x. Again, that's straight out of the power rule. Then you multiply them together, and you end up with cosine of x squared, the derivative of the outside, leaving the inside alone, times the derivative of the inside. Now, when you look at this equation, you still have, the nesting dolls, or, the inside-outside rule, the chain rule. You have y is equal to x squared, the quantity of x squared, times 3x, or plus 3x, plus 4, all raised to the 30th power. Now, again, so you got an outside function. You could think of this whole term here as separate. So you want to take the derivative of this entire quantity first, and then take the derivative, leaving the inside alone, and then take the derivative of the terms on the inside. So, and when you take the derivative of the terms on the inside, you're going to have to look at them as through the terms of the power rule. The sum of the derivatives is equal to the derivatives of the sum. So the derivatives of each one of these terms on their own. All right. So when you consider the outermost function here, you've got the quantity of x squared plus 3x plus 4 all raised to the 30th power. Using the power rule, you end up with 29, or excuse me, 30 times that quantity, leaving the inside alone. 30 times the quantity of x squared plus 3x plus 4 all raised to the 29th. Again, still following the power rule. Now you want to look at the inside. We have the derivative of x squared is just 2x. The derivative of 3x is just 3. And then the derivative of 4 is just 0. There. Now, and you can take this as, the quantity of these terms. Take the quantity of those terms, and then you multiply them together and simplify. So you got the first term of 30 times the quantity of x squared plus 3x plus 4 raised to the 29th power times the second, which is just the derivative of the inside, which is 2x plus 3. So that's our first two examples. Now these last times I'm not going to give you the actual answer at the end, but I will show you the problems. So in this first example, you've got a few different terms here that I want you to look at. So you got the cosine of e raised to the 2x. So in this case, you've actually got 3 nesting dolls. All right. You've got a term here you're going to take the derivative of. Then you've got this insidemost term, and you've got this outermost term. All 3 of those are going to require you taking a derivative. So if we go through this, the first term, this inside outside works both ways. So we can start in the inside or start at the outside. Just keep track of what you're doing. So the derivative of 2x is just 2. The derivative of e to the 2x, again leaving this version of the inside alone, is just e to the 2x. The derivative of e to the 2x is just e to the 2x, leaving the inside alone. And then the derivative of the outside, again leaving the inside alone, is just negative sine e to the 2x, again leaving the inside alone. And you multiply these 3 together, and you end up with the derivative of y is negative 2 times e to the 2x times sine e to the 2x. So this is each one of the terms just simplified and made a little more easier to read. Now in this term, very similar to one of the examples we gave on the previous slide. So we have x to the 5th is equal to 3, or x to the 5th plus 3x plus 4 all raised to the 22nd power. I like these big numbers because they're not easy to just FOIL them out. So the chain rule is probably one of the best ways of doing the derivative on these. So the derivative of that, you take, again, the sum of the derivatives is equal to the derivatives of the sum. So again, we've got what is going to be 5x to the 4th. Then the derivative of 3x is just going to be 3, and derivative of 4 is just going to be 0. That's the inside. And when you consider the outside, think of this as just one term. And again, you're just using the power rule. Again, this whole thing is a quantity. You have 22 times this entire quantity raised to the 21st power. So let's see how this worked out a little bit neater in the PowerPoint. So again, all we had there was 2 nesting dolls. Oh boy, that's messy, but what you have is, the outside 22 times that entire quantity, leaving the inside alone, raised to the 21st power. And then you've got the derivative of the inside, which is, again, 5x to the raised to the 4th power plus 3, again, and 4 is 0. You multiply it together, you end up with this quantity. Once you've multiplied it, let me get rid of some of this, see if this works for me. I guess I'm not sure how they get that. Now, last bit. And so you can see here that the power rule is used throughout the entire chain rule process. So in order to understand the chain rule, you have to understand how the power rule works. So again, This is Professor Cummings. I want to thank you for watching, um, and I'll see you in class.